Okay, so recursion versus iteration. Okay, so now we have learned two major processes that are used quite often. Two major techniques, recursion and iteration. Let's look at what are the differences between them, right? So recursive process, remember we are always deferring operations. We are trying to break down the problem into the simplest problem while not solving the step beforehand. Then once we reach the terminating condition, right? Then we will start to do all the deferred operations. Usually it's more straightforward. I would say usually, definitely more elegant to write the code. It looks nicer usually. Okay, but when we talk about iterative process, right? All your whatever value is inside the loop at that point of time, whatever that's inside the iteration, it will run at that point of time. You will just update your values accordingly. You update your values instead of creating a deferred operation. Okay, it's usually more efficient as well. Alright, but usually then it doesn't look so nice. Alright. Okay, so depending on your use case, some students will end up preferring recursion, some will prefer iteration, but of course during exams you need to see what the question wants you to do. Okay, so looking forward, right, there are different ways of performing computation. It can consume dramatically different amounts of resources. Alright, so when we design programs, right, the first two things is that they must work. Okay, most important is must work. If there's no point talking about efficiency of program if your program can't work. And for efficiency, we look at two things: the time taken, the time complexity, and then the amount of memory used. Okay, so in an ideal world, right, your code will work. You will be very efficient in terms of the time taken, very short time, and also it uses the least amount of space. Alright, so this is what we are aiming for. Okay, so let's look at how we measure time, right? Okay, we count the term in terms of number of steps executed. Assume that steps are executed in sequence, and then we assume that each step takes a constant time. Alright, so this is how we think. That means every step your program take, we just assume the same amount of time, regardless of what's the operation that's being done over here. Okay, so let's look at how we can use this to help us to calculate. Alright, first thing first, depending on the value we choose, right, the complexity might change. Okay, so for example here, I have a simple linear search. What a linear search is, in this case, I have a list or sequence called L. I'm looking for the character S. Okay, so I will run through every single item in L and check whether each item E matches X or not. If it matches X, return true. If not, at the end of it, out of the loop, once it runs through every single item, that means it can't find anything, you just return false. Okay, so best case scenario, X is at the start of the list. For example, let's say a list of numbers from 1 to 9, list of integers from 1 to 9. You're trying to find 1, and then you can find it right at the start. Okay, so that's the best case scenario. The worst case scenario, let's say again you have a list of numbers from 1 to 9, but you're trying to find 10. Okay, so that's a worst case scenario because your function here will run through 1, 2, 3, 4, 5, 6, 7, 8, 9, and then realizes that you cannot find 10, you just return for you false. So the average case X is in the middle. So let's say you are trying to find 5, for example. So 1, 2, 3, 4, 5 steps, and you just return you true. Okay, but for the sake, of course, if we use the best case, if we code the best case each time, right, then our code will look artificially good, artificially efficient. Okay, we usually for this will code the worst case. All right, so we use the worst case scenario. Basically, we are preparing for the worst scenario here lah. So that will give people a more realistic expectation. It's a bit like under promise, over deliver. Alright, let's look at this. Let's look at what's the order of growth of this function here. Okay, so right now here I have this function g and return n square. So you notice that no matter what value of n you use, it will just run it one time. You sub n as 10, sub n as 1000, you just square it. Alright, so this is just one step, no matter the value of n. So in this case, right, your big O notation is O1. Okay, capital O then 1. Basically, no matter what value of n you put inside, your function will just be one step. Okay, next let's look at this one over here. This one's a bit more interesting. fact n. Okay, answer equals to 1. While n is more than 1, answer equals to answer times n. Then n drop by 1. Okay, so if we look at this over here, there are two operations that involve n. Okay, first is this answer equals to answer times n, so that's one operation, and then n equals to n minus 1. Okay, so over here, right, there are two operations. So this answer equals to 1 is over here, and then this 2 times n minus 1, because I will run this code until n is equals to 1, so I run it n minus 1 times. So for each time, I will basically do two operations involving n. So therefore it's 2n minus 1. 2 times whole thing n minus 1. Alright? Then return answer. So it's plus 1. Okay, so this is always plus 1. Okay, so look at the worst, which one will cause your number of operations to grow by the most, right? It's actually this 2 times n. Okay, because everything else is a constant. Okay, so this is O(n). Okay. Alright, so I just take the largest possible growth factor here. In this case, this is n. Okay, I can drop the 2. Okay, because once you go higher numbers, right, your constants don't really matter anymore. Okay, let's look at a more complex one. We have this function here. Okay, define fx for I in range 1000, answer equals to I. For I in range x, answer plus equals to I, or answer plus equals to 1. For I in range x, then this is a double loop for I in range x, and for j in range x, answer plus equals to 1. Okay, so let's look at this one first. For I in range 1000, answer equals to 1. This is a one-step operation. Okay, whatever the answer is, whatever I is, you assign to that value over there. Okay, for I in range x, answer plus equals to 1. So basically, if you double this number, you will need to do this step twice. You will need to double the number of times to do this step. Alright, so this is basically this section here is O(n). Okay, for this one here, this is a double loop. So for I in range x, for j in range x, right? So answer plus equals to 1. Okay, if you think about this, right, this is x times x. Alright, so that means for, let's say you are ranging from 1 to 10. So what I do is that you will first take from 1, you take for I equals to 1, then you take for j equals to 1, then 2. So I equals to 1, j equals to 1, then 2, then 3, then 4 until 10. Then now for I equals to 2, then j will take 1, 2, 3, 4, 5, 6, 9, 10. Then for I equals to 3, so on and so forth. Then it will until for I equals to 9, then j will take 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright. So in this case, your maximum growth here, okay, the first one is 1000, that's fine. You just do this 1000 times. Then x, because this is basically, if you double this will increase by x times. So the key here is this x squared here, right? So this x squared is the main growth factor. So in this case, your order of growth is O(n) squared. Okay, so that's how you read it. Alright, so rules to calculate order of growth. Ignore the constants, because when the constants they become irrelevant when n becomes very, very big. Okay, ignore the constants multiple. Okay, so when n is big, it doesn't matter if it takes 3000 hours, 6000 hours. Always look for the item with the largest growth rate, because the item with the largest growth rate is the one that contributes to the most to your growth. Alright, okay, so that's all for iteration. We'll stop here. You can continue working on your LT and tutorial.